Let's talk about problem sets. There will be 2 problem sets this month, both due at the end of the month. We'll first take a look at the problems from the previous year. The ones that will be posted this year will be almost the same. Submit all work. There's submission details now on Brightspace. First problem, convert a decimal number into a binary, 8-bit sign magnitude. What is sign magnitude? I did not mention this in the previous lecture. Basically, you encode the absolute value in the binary, and then the leftmost bit will be the sign bit. So put this problem asks for 68. In this case, it doesn't matter if it's a sign magnitude or just the magnitude, because there is no sign. Minus 83, the leftmost bit will be 1. The rest, just the same. Now, keep in mind, this is not used in most systems. In most computing systems, the way to encode the integers is different, as we discussed in the lecture. Perform the calculation in 8-bit sign magnitude arithmetic. I think what it asks you to is just to perform it like on paper. Try to do this, see if you understand the process, how you add the numbers. Repeat A in 2's complement, and then compare the results, see what happens. Second problem, convert this real value to the 32-bit floating point representation. Now, we talked about how to convert from the binary to any other representation, but we did not yet talk how to convert it to the binary. We will discuss this today. Stay tuned. What's the decimal representation of the following 30-bit value? So that's the one that we already talked about. You'll need to work on this. Either you find the converter somewhere, or you code it, or use the calculator. You have several options. Either way, it will have to match the formula on the Wikipedia page for the IEEE standard. Now, all right, it's number 3. Just keep in mind these numbers will be different in the actual problem set, so download the PDFs. Consider a floating point system that uses 11 bits to store real values as follows. Now, this shouldn't be a problem. We discussed the one that had 8-bit for exponents and 23 bits for mantissa. This one, 4 bits for exponent, 6-bit for mantissa. Mantissa is the fractional part. What the value of the bias be? What should the value of the bias be? Now, we did not really say what bias is, but if you remember, there was this magical number 127 that's subtracted from the exponent. In the Wikipedia page that explains exponent encoding, it says the single precision binary floating point exponent is encoded using an offset binary representation, with a 0 offset being 127, also known as the exponent bias. So the way that it's obtained in this case, the exponent is encoded as 8 bits. That's 2 to the power of 8, that becomes 256. You divide that in half, that gives you 128, and subtract 1, which becomes 127. Now, just for this assignment, repeat the same process. Just keep in mind the exponent is now not 8 but 4 bits. So 2 to the power of 4, divide by 2, subtract 1, What does it give you? What is the most accurate representation of 0.7 in this system? So same thing, we'll need to convert 0.7 into the binary. We'll talk about this today. What is the next largest number that it can represent, that can be represented? Essentially, what you want to do is to add the smallest fraction to the mantissa. So if mantissa is 1 over here, add 1, just add 1 to the rightmost side of the mantissa, unless the whole mantissa are ones. If the whole mantissa is filled with ones, then we'll be changing the exponent. I hope it explains the process. What is the next smallest number that can be represented? So the same thing, just go the opposite direction. Comment on the spacing between values. Is it always the same? We already discussed that, right? So the spacing depends on the exponent value that is set here. For the following problems, analyze the problem in terms of input and output and develop an algorithm to solve the problem. Write your algorithm in pseudocode. Now that seems scary. In this new assignment that we will have, there will be no pseudocode. Let's just do Fortran now, because you need to practice. Before we continue, it's actually easier to do pseudocode, because what this asks you to is to use your common sense to say which values are given to you and which values you need to accept from the user. And the pseudocode will look like this. Take from the user these values, then plug them into the formula and produce the output. So in a way, that's a very simple pseudocode. There's no conditional statements, no loops, like no structure. It's just the flow, a straight linear flow of the program with like 3 steps. Take the values, compute, print it out. Again, use common sense for these formulas. Probably, pi is the constant. G is the gravitational acceleration. Whether it's a constant or not, you decide. It's not really a very constant value. If you go to different parts of the world, it will fluctuate. But it's usually, for the purposes of school, is 9.8 meters over second squared. So it's fairly constant value. So what's left here is L. I'm solving the problem for you already. So your goal here, invoke a user prompt, type something, please enter the length of the pendulum. Take this value, read it into a variable, plug it in here, compute the result. Now B is slightly, we're gonna make it slightly more interesting. Now here it asks you to compute the formula for the potential energy and the kinetic energy. Keep in mind that these are not 2 values here. PE just stands for potential energy. It's kind of like a 1 variable, not a common mathematical notation. Usually in mathematics, you would see something like E with a subscript P. This may be confusing for mathematicians. Gravitational acceleration is usually assumed to be constant. But here, look what the problem says here. The potential energy of an object due to its height above the Earth's surface. And when you talk about these objects, you would think like, oh, it might be like an airplane or a space station or even the moon. For those objects, the gravitational acceleration is different because they're so far away from the Earth that the effect starts to play a role. If there's a climber who climbs Everest, acceleration will also change, but it's not enough to feel it. Now, for a space station, that's already a considerable change. So let's look at the following. There is this article on Wikipedia about gravitational energy, and it gives two formulas. So there's this formula. Now look, this G is the large G. It's a gravitational constant, not the acceleration, but it's a much more fundamental physical value, which never changes. M is the mass of one object like Earth, the other M is the mass of the second object, like a person or a space station. R is the distance between their center points. It says close to the Earth's surface, the gravitational field is approximately constant. Yes, but in a very narrow stripe. So again, like you go up the building, mostly constant. You go up to Mount Everest, already starts to change. If you go out into space, definitely changes. So use either formula that you'd like, but if you use the one that is made for close to the Earth's surface, then in your code, check if you're close to the Earth's surface. Make a conditional statement. Use your own common sense to define what it means to be close to Earth's surface. Also, consider the units that you will be using. Are you using meters? Are you using kilometers? Are you using maybe feet? Consider that. Write the code in Fortran. Make it work. Let's talk about the second problem set. We'll just do both at once because the second is due on the February 1st. We'll make them both due at the end of the 31st of January. Write a Fortran program that, given 2 points in 2 dimensions obtained from the user, computes and displays the slope-intercept form of the line passing through the 2 points. So consider 2 special cases. There might be a vertical line and a horizontal line. So there's the only difficulty here. Now, it asks to give the F08 file extension. This was used last year in the course. We're using .f90, not because we're using older language, but because F08 is not picked up by the build tools like CMake. It's not really a standard extension for Fortran code. A toll bridge charges $4 for passenger cars, $8 for buses, $6 for trucks under 10,000 pounds, $10 for trucks over 10,000 pounds. Write a Fortran program to output the appropriate toll for a given user input. C for a car, B for a bus, T for a truck. If truck is entered, prompt the user for a character, lesser or greater. Your program should use a select case statement. So select case, we'll talk about this today as well. So let's do the simple material first. Now, select case statement. It's the same as the conditional if operator. It is used for clarity of the code. I was trying to find good examples from real world code, and I didn't find any. It seems that usually programmers prefer to use if then. Still, this is part of the course, so we will look at this material. I prepared the following example. A small program that selects the name of the community based on the airport code. So first you're asked to enter airport code. It's a 3 letter code, and then using the select case in this type of syntax, one of the 4 choices is made. So either St. John's for YYT, Calgary for YYC, or Montreal for Yule. If none of these matches, the default is unknown. It's pretty much self-explanatory. Select case, then in the parentheses you put the variable by which you're making the choice. In this case, the variable is a string. It's a whole array in the memory, and it's treated in a special way. It's not like a simple singular entity that we had before, like reals and integers. Now it's going to be an array. It will get a special treatment when comparing strings. Strings, they have to be compared basically just like one letter at a time to see if all the letters match in the string. So it's a special subroutine that exists implicitly, that Fortran just kind of provides the moment you type the comparison operator. And then we have another variable for the output, a 20 letter long community. While the size cannot be exceeded, there can be shorter strings that can fit in this variable. So the select case syntax is very much self-explanatory. Case YYT, and some instructions follows. There can be more than one. Case YYC, same thing. There can be more than one instruction. They can be loops, if statements, anything inside the case statement. And then there's a default statement and end select. So we do this using this select case syntax. In the end, we print out our result. We also repeat this using if statement, just for the purposes of demonstration. Compare the syntax, see which one you prefer. Let's run the code. Enter code YYT. And then converting with select, we get St. John's. Converting with if, we get the same result. And I think no further demonstration is necessary. If that was not on the list, it's not picked up. And finally, there's something that I want to try. I'll put 4 letters. And no error is produced. I'm actually curious now, what is the result that we read? So let's put another write statement here. Let's write back the code that we received. And only 3 letters is actually accepted. There is more to the case select case syntax. In general, this is the general form. There is more when it comes to picking the ranges. So for example, this is the example for the integer, which only has cases matching to one of the possible variants. So 1, 2, 3, 4, and default. We have the case, the one we just did with the character. Here, see how the length of the title varies. There is one that has 4 characters, other has 3 and 2 and 2, and the default. Now we're doing the ranges. So this syntax, the column, will be anything that's less or equal to -1. The other option is 0. The other option is anything that is greater or equal to 1. And then similarly, you can do the same thing with the individual characters. So anything between A and J, anything between L and P, or anything between U and Y. So this comma stands for or. And same thing with the numbers. You can have 2 ranges. So this range or that range. or two choices in the same case statement. So either 3 or 5. For the if statements, you can write something like this: if A not equal to B or C equals 5, then do something. Else, if, and put a different condition. It can be a fairly long logical expression. If C equals to 6 and A is greater or equal than 7. So learn that syntax for both constructs, for if statements and the combination of logical expressions. Keep in mind this symbol, so not equal, equal, and then of course greater and lesser. Both constructs can be nested, so they can be if statements within the if statements. Also, let's look at this second statement. You can split it up and make it into two separate if statements like this. So if C equals 6, then we'll need another then here. If A greater or equal than 7, then condition is met. And if, right? So this is equivalent to combining them with and, because if the first one is not met, nothing works out. If the first one is met but the second is not met, again the condition is not met. The or condition, you can also split the statements, but you'll have to go like this: if A not equal to B, then so we have condition 1, and if C equals 5, then, and same thing, condition 1, and if. So this would be equivalent to this very first if statements. So look how they can be split, how they can be nested, and how the logical expressions can be combined with and or. There will be something like this on the term test. So let's look at another topic. In the context of conditional expressions, we deal with Boolean variables, Boolean values, and we will look at them now. But before we get there, very quick talk about variable names. Let me show you here on the screen the problem that I encountered. So I wanted to create the logical variables A, B, and C. And then A I assigned to true, B to false. And then I wanted to do something with C, but my editor, this is GNU Nano, somehow decided that this looks like a comment because it's a line that starts with C, and then the older Fortran syntax, C was the comment line. What happens is that line that starts with C is no longer a comment if you're using this new, what's called the free-form syntax. So the comments in this new Fortran syntax start with the exclamation mark and not C. So C will be considered a variable. So here, let's talk about the variable names. And more generally, there is a concept that's called identifiers. So identifier will be a name for the variable or a function or subroutine or a program or a constant. Now, very briefly, it just has to start with the letter A through Z, uppercase or lowercase. By the way, case doesn't really matter in this case. Maximum 63 characters of length. I haven't tried what's going to happen if you take a longer one. Maybe only the first 63 are actually considered, or maybe if you take a longer one, it will throw an error. We don't know. Characters other than the first, maybe letters, numbers, or underscore character, but not spaces, and not anything else. So this is all that you're limited to. Note that the underscore character is often used in identifiers to separate words. Yeah, okay, so that's fairly common. Fortran is not case sensitive, so that we already mentioned. And it's important to use meaningful identifiers unless your program is teeny tiny, where you have like usually I, J, K, L, M, though like they are integer indices, and variables that start with like A, B, C, D, they are usually real valued numbers. In the old Fortran, if you had a implicitly declared variable that starts with A, B, C, D, and so on, they become automatically reals, and anything from I, they become indices, because this is common in mathematics to use I for an index and J for the second index and so on. So these are identifiers. Let's go back to our Booleans. Now Booleans are, it's a very big topic. We will only scratch the surface of it. Let's try to print just the assigned Boolean values. Let's see what will happen. So it prints as T for true, F for false, and T for true C. So you can combine logical expressions. Let's now make C A and B. So both A and B have to be true in order for C to be true. And we will print. And of course, this results in false. Now, I will not make you go through every tiny combination of those, but I will refer you to the following pages. First of all, there is some discussion of a logical type in Fortran. It's fairly simple type because it can only take two states, true or false. So this page is very short. There is also, it's possible to allocate just one byte for the logical because it really needs just one bit, but the processor cannot really use just one bit. It needs a bigger chunk of memory, which is byte. And you can have a logical variable as 1 byte and 2 bytes and 4 bytes and 8 bytes using this syntax. The way that it functions in the code, the way that it's rolled in the code does not change. It's very just like an internal representation of it that changes. So in reality, it might be needed only if you transfer data from one system to the other, where the sizes are different. There is also a large article on Wikipedia about Boolean expressions in general. So they talk about the use of Boolean expressions in computer science, and that's more fundamental. It's a talk about Boolean functions. There's operators such as not, which invert the variable, and an or. It's pretty much self-explanatory what they do. So, and then there is even much bigger article called propositional formula, and now that's in the area of logic. That's already like the area of mathematics that we're going into. For example, there is something called De Morgan's law, and it goes like this. If you're trying to negate an expression that looks like B or A, and we're trying to negate this whole expression, we can also rewrite it as not B and not A. That's De Morgan's laws. Now they are formulated here as laws on sets. Same work for Boolean logic. Before we jump to dealing with integers, let's quickly mention one more thing. So operator precedence in Fortran, especially the one that deals with the exponentiation. So let's give it the following expression: 3 to the power of 2 to the power of 4. By the way, we have Mathematica for it. Let's go and do this. 3 to the power of 2 to the power of 4. What do you think the result will be? There it is. So it is equivalent to 3 to the power of 16. So note how these higher operations are computed first, and then the exponentiation of 3 happens last. So if we think about the order of operations in this string, it will go from right to left. So the exponentiation operation, first of all, it has a fairly high precedence over everything else. So this will be computed first in all the other algebraic expressions, and then it will go from right to left. Unlike some other operations like subtraction, which will go from left to right, for example. And then we'll compare it just for clarity. So we'll put the left side in the parentheses. And then in the parentheses, of course, they will take the precedence because parentheses have the highest precedence of everything. And as the result on the right, the result is shown. So first, the default expression is what we got in Mathematica. It's computed from right to left. And then this smaller expression will happen if you take the square of 3 first. This will be 9 to the power of 4. So that gives you a different value. So that's was a very short talk about the precedence of the operations. It's something that was in the lectures from last year. It's a fairly important topic. Those are the arithmetic operations that you would see in Fortran. And parentheses from innermost to outermost, they take the highest precedence. Then we have exponentiations, which are performed from right to left. And I remember I saw a table somewhere on the internet that gave the wrong idea. It just had like the wrong statement about it. Then we have multiplication and division. Basically, they just go from left to right, as they appear. And finally, addition and subtraction. I don't think addition really matters in terms of the direction in which the operation takes place. I know in C and C++, the compiler is kind of like free to shuffle them around. Subtraction matters in terms that there is the negative sign. So if you move them around, you also need to move the negative sign along with the number. But yes, so use parentheses for clarity. And if something comes up on the problem set or on the exams, if you use parentheses to clarify the order of operations, that's fine. So another topic over here is the division of integers. Now, if we have the two integer variables and some operations are made on them, the result will also be an integer. even if we divide something like 2 over 3. The question is what will happen. And what you would expect here, and it's more of a feature of a processor, that the decimal part will be just thrown away. So let's divide 2 over 3. If you were to round this number with the common rounding rules, it would round up. But in the arithmetic in the CPU, what it does, it just throws away whatever decimal part there exists. So here's a small code that explains what will happen with the integers. We will have 2/3, which would normally give us something like 0.6666666. And with the integers, it's rounded to 0 because the decimal part is thrown away. For the negative, same thing. So we would get negative 0.6, but the decimal part is thrown away. Remember, in integers, we don't have negative 0. It can only be 0 without any sign. And this is what they get here on the right. So try to calculate this in the computer and you will get exactly 0. Now 3 over 2, it's 1.5. Throw away the decimal part. We're left with 1. And finally, negative for the same thing. We would get negative 1.5, but thrown away the decimal part gives us negative 1. There will be a question on the test that will go something like this. What is the result of that statement? And you'll be given integer division, something like maybe 7 divided by 8. You have to be able to tell the outcome of this calculation. This is a fundamental knowledge. This is how most CPUs work these days. The operations on the integers, they're fairly standardized. It does compile, although it complains now, it gives warnings. So conversion from integer to logical, it doesn't like it. But let's see the results of these conversions. So first of all, remember a over here, it's a real typed variable. I'm trying to assign it to 2/3, but what I get here on the right side is 0. How does that happen? So over there in the program, 2 is an integer, 3 is an integer. Their division results in the integer result, which is 0. And then this 0 is assigned to a, converted to real, and it becomes a real valued 0. So this is a possible source of errors. To solve that, you need to divide the real numbers in the first place. So 2 real divide over 3. At least one of them has to be real. Then the real values will be divided. If it's mixed, they will be sort of like promoted to reals, both of them. At the next line, so a is equal to 2. Yes, we get 2 in the a. B is equal to 3. Yes, we get 3 in the b, but there's an additional conversion operation from the integer 3. Sometimes you want to avoid those conversions because they take up processor time. We divide those real values, which we already know what's going to happen. We'll get 0.66666, and assign it to I, which is integer, and then it's implicitly converted to an integer, which makes it again 0. Finally, let's look at the logical variables. So first of all, we already noticed that the compiler will throw a warning. It's not really a good way to assign a number to a logical variable, because those are completely different types in terms of their meaning, right? So one is just true or false, it's not a number. But still, we're trying to, let's assign it this 0, and this gives us false. Assign it with 1, and it gives us true. Assign it with -1, and it still gives us true. The bottom line, assign it with anything other than 0, and it's true. 0 will be false. So another topic that we need to discuss is how to convert arbitrary floating point value into the IEEE floating point standard. There is a tool online that does that. You just enter the number that you want to convert. Let's try 33.7, and it gives the answer. Now let's retrace the steps in Mathematica. At this time, let's assume for a moment that you already know how to convert the integers. And in Mathematica, there is a function called base form. It can do that. We'll convert 33, which is the integer part. We will also convert the decimal part, 0.7. Let's talk about how you go from the binary to 0.7. So you start here on the left. It's 0.1, and that gives us 1 to the power of 1 over 2 to the power of 1 plus this is 0, that doesn't count. So the next one will be 1 over 2 to the power of 3. We'll continue like this. 4. So 1, 2, 3, 4, 5, 6, 7, and 8 we include. 7 and 8. 9, 10, 11, 12 we include. 11, 12, 13, 14, 15, 16, 15, 16, 17, 18, 19, and 20. 19 and 20. Let's compute 0.7. Perfect. Not always it will be the exact number. It is actually not the exact number, but it's close enough. It's the closest that can be possibly achieved. Now, this is not yet the IEEE form. Let's see how we get this into the IEEE standard. To start with, we need the whole number together. So let's do base form 33.7, and it just combines the integer part on the left with the decimal part on the right into one number. Now we'll need to count how many positions do we need to move the dot to arrive to the very leftmost one. So we'll move it 1, 2, 3, 4, 5. This will be the exponent of this number. Let's divide it by the 2 to the power of 5. And we get this, which has 1 on the left. This will be the implied one of the mantissa. Remember, if you remember from that formula, there is always that 1 in the sum. Then whatever is on the right here is actually the mantissa. So if we look on the converter on the right, 0, 0, 0, 0, 1, 1, 0, 1, 1, and compare it. 4 zeros, 1, 1, 0, 1, 1, and then 2 zeros, 2 ones, 2 zeros, 2 ones, 0, 1. And let's look at the right. 2 zeros, 2 ones, 2 zeros, 2 ones, 0, 1. Now, the exponent. So we figured it out, it's 2 to the power of 5, but there is also a bias of 127. So what we do is 5 plus 127, we get this integer, 132. Note how it's already displayed here on the right. We convert this to binary, and that will be the bits for the exponent. So 1 for zeros, 1, 2 zeros. 1 4 zeros, 1, 2 zeros. The only thing that's left is for us to learn to convert integers to the binary and fractional parts to the binary. Integers is easier. Let's do 33. So take the remainder of the division of 33 by 2. It's 1. This will be our least significant bit. Subtract that 1 from 33. So 33 minus 1, divide by 2. Then repeat the process. So remainder 0, 16 minus 0 over 2, 8. Remainder 0, over 2, 4. The remainder is 0. 4 minus 0 over 2. Actually, let's write this down here. Remainder divide by 2, and finally remainder is 1, and there is nothing left. So let's get our numbers, the results of those remainder operations. So there's, okay, so 1, 0, 0, 0, 0, 1. And this is exactly what we got here in Mathematica. So 1, 0, 0, 0, 0, 1. Now to convert the fractional part into binary, it's a little bit trickier. The explanation is given on this page over here. So let's look at converting the fractional part to the binary. There is a page that explains the process. I will put the link somewhere over here. In brief, it's fairly simple. We'll start from 0.7, multiply it by 2, get the result. Look at the leftmost number, record it, throw it away, and then continue multiplication. Look at the leftmost number, record it, continue multiplication. Record the number, throw it away, continue. record the number, throw it away, continue. Record the number, continue. Record the number, continue. Record it, multiply by 2, record it. If it's 1, we throw it away, continue. At this point, you can notice that the sequence is repeating the last 4 digits that we got, which is 0011. So it will continue like this indefinitely. Now let's compare to the result of Mathematica. It goes like this: 1 0. We also have 1 0, and then this repeating fragment 1 1 0 0 1 1 0 0 1 1 0 0, and so on. So that's the same that we get: 1 1 0 0 1 1 0 0 1 1 0 0, and so on. Again, so how to convert this fraction back, it was already shown. Now you have the explanation for the algorithm, how to convert the decimal portion to the binary, how to convert the integer to the binary, how to combine them, how to find the exponent, how to get the proper integer for the exponent, considering the bias. And also don't forget the sign bit. You have many ways to double check your work. There's online tools like this. There is some very good explanations how to make the conversions. Let's talk a little bit more about the conversion process. We will look at the problem number 3 on the first set. So consider a floating point system that uses 11 bits to store real values as follows. By the way, there are systems that use 16 bits, that's called half precision floats, and they're used for machine learning. But still, so we have 1 sign, 4 bits for the exponent, 6 bits for mantissa. What should the value of the bias be? Now, to get the value of the bias, we take 2 to the power of 3, which is 8, minus 1 makes it 7. So 7 is our bias for the exponent. Let's remember that. And we'll get to the next part. What is the most accurate representation of 0.7? So let's do that. We will try to use a simpler method. You can even call it cheating, because it will allow you to complete this task without fully understanding what's going on. So using a converter, convert 0.7. Now you get the bits. Now forget about the binary representation. Look at the bits for the mantissa, and we'll need 6 of them, starting from the left. So mantissa will be the following: 0 1 1 0 0 1. Those are 6 leftmost bits on the conversion. The mantissa will stay the same. Now for the exponent, we already figured out that the bias is 7. Now we do this: base 2 logarithm of 0.7 round this down, so that becomes minus 1 plus 7. It's the bias. 6 will be your exponent. In binary, that's 110. And then as a result, we get the following. So 0 for the sign. Now 4 bits for the exponent. That will start with 0, 1, 1, 0. And then for mantissa is what we established. Now let's convert it back. So for the exponent, we already know what it's going to be. 6 minus 7 times a certain sum. So 0 over 2, that's for the first, 1 over 4, 1 over 8, 0 over 16, 0 over 32, 0 over 64. 0 over 64. And 1. There is also this implicit 1. And there you go. So the representation of 0.7 using the binary system is this, and we have a method to double check it. Now keep in mind that in the actual assignment that we will be doing, the number of bits will be different from this old assignment, but you now have a conversion process where you avoid converting the decimal part, because you can just have an automatic online tool do this for you, and mantissa will be the same, just the exponent will be different. This wraps up lecture 5. We'll continue on Friday. Stay tuned. Now you have problem sets to work on. If there's any questions, we can discuss those on Wednesday during the online WebEx meeting.